Approximating pi with the beta function. The beta function. The beta function is also known as an Euler integral of the first kind, and it's given by a multivariate or two-variable function, here in terms of x and y, by the integral from 0 to 1 of t to the x minus 1 power times 1 minus t raised to the y minus 1 power dt. The integrand's nothing special, it's going to work out to be some polynomial, so let's do an example with this beta function. Let's let x and y both be 5. Letting x and y both be 5 in the function, we get the integral from 0 to 1 of t to the fourth times 1 minus t to the fourth dt. Now, again, this is not a terribly difficult integral to do, so what we're actually going to do is expand out that binomial using the binomial theorem, and the binomial theorem expansion makes use of Pascal's triangle. Here, I just build the triangle up to the row that I need here, and this row will represent the coefficients of my binomial expansion. So 1 minus t all raised to the fourth power will have 5 terms in it. 1 minus 4t plus 6t squared minus 4t cubed plus t to the fourth. So if I went ahead and multiplied that polynomial with t to the fourth as in our integrand, we would get t to the fourth minus 4t to the fifth plus 6t to the sixth minus 4t to the seventh plus t to the eighth. Integrating a polynomial just makes use of the power rule for integration. Substituting this into our integral, and then finding the antiderivative for each term separately. T to the fifth over 5 minus 4t to the sixth over 6 plus 6t to the 7th over 7, minus 4t to the 8th over 8, plus t to the 9th over 9, evaluated from 0 to 1. Now evaluating at 0 will just give us 0, and evaluating at 1 will give us a series of fractions that will add up to 1 over 630. So our beta function, evaluated at x equals 5 and y equals 5, gives us 1 over 630. But what does this have to do with pi? That's coming soon. But first, something a little explicit. The gamma function. There's a connection here to the gamma function. So let me remind you what the gamma function is. It's an integral from 0 to infinity of t to the x minus 1 power times e to the negative t dt. And this is the same thing as evaluating x minus 1 factorial. So the beta function, in terms of x and y, which I'll remind you is this integral, you can see a similarity in some parts of the integrand there, but the surprising relationship is that beta of xy is equal to gamma x times gamma y over gamma of x plus y. And this turns out to be a very useful relationship in calculating values of either the beta function or, in some cases, the gamma function. And the gamma function can be written in terms of its factorial notation. So here, let's reevaluate the problem we did earlier, the integral from 0 to 1 of t to the fourth times 1 minus t raised to the fourth dt, which is beta of 5. But now we're going to use the gamma function to evaluate it, and gamma of 5 would be 4 factorial, where gamma of 10 would be 9 factorial. And expanding that out, we can merely see what the factors look like and begin to cancel some things in this fraction. What we're left with is the fraction 1 over 5 times 2 times 7 times 9, which is 1 over 630. Now that was a much more efficient way of calculating the beta function, so this formula connecting it to the gamma function is very useful. But again, where's pi? For that, we're going to have to do some integral comparisons, and we're going to introduce a similar integral to the beta function integral we were just calculating. So let's consider an integral that's similar to this, except where the integrand is divided by 1 plus t squared. We can make an argument here using the integrands. 1 over 1 plus t squared will be less than 1. And that's because t is going to be in the interval from 0 to 1, so t will be a fraction, and therefore 1 plus t squared will be a positive number, and it'll be less than 1, except for when t is equal to 0. So if we substitute that into our integrand, or rather make them the two integrals here, we can make the following inequality, that our integral I is less than b. So we can say that the integral I, which is the one that is divided by 1 plus t squared, will be less than 1 over 630. Now, evaluating that integral is also not terribly difficult to do. If you remember, that numerator works out to be a nice long polynomial, and we have it divided by 1 plus t squared here. We're going to use a little bit of long division of polynomials to reduce that integrand down to a more manageable form. And sparing you some of the long division details, we get a quotient here of t to the 6th minus 4t to the 5th plus 5t to the 4th minus 4t squared plus 4 with a remainder of negative 4. So entering our quotient plus our remainder over our divisor into our integrand, we now have a much more manageable integral to deal with. And so moving through the polynomial part of that, we can just find its antiderivative using the power rule for antiderivatives or integrals. And then that last component will evaluate to an arctangent. And we're going to evaluate this again from 0 to 1. What this works out to be is, surprisingly, 22 over 7 minus pi. There you are, pi. So now, setting this into our inequality, we have 22 over 7 minus pi is less than 1 over 630. And manipulating that around, we can get a lower bound estimate for pi. 22 over 7 minus 1 over 630. So that's our lower bound estimate for pi. And we now want to find a upper bound for pi so we can squeeze pi in between two numbers. So next, what we're going to show is that 1/2 of the integral b is actually less than I. And since, again, t is an element between 0 and 1, 1 plus t squared would be less than or equal to 2. So the reciprocal of this would tell us that 1 over t plus 1 plus t squared is greater than or equal to 1/2. So now, using that in our integrand, we can set up the inequality that our integral I here is greater than the integral from 0 to 1 of t to the 4th, 1 minus t raised to the 4th, all over 2 dt. And the integral to the left is just 1/2 of the integral that we evaluated earlier. And so now we can get an upper bound for our pi. Pi is less than 22 minus 1 over 1260. That is our upper bound. And if we want to get a better idea about just how close that is squeezing between pi here, looking at the decimal values of these fractions will give us a more numerical sense of just how accurate our estimation is. So, using the fraction notation, we have our inequality, and pi sits right between these two numbers. The number on the left is approximately 3.1412, where the one on the right is 3.1421. And since pi is 3.141592653589799323 and so forth, this is a nice estimation for pi for all practical purposes, and it was due in part to the beta function. Now, my challenge to you is, can you get a better estimate on pi, a better approximation using the beta function? How do you modify our problem from today? I hope you liked this video. Please hit that like, subscribe, and notification bell for more videos, and stay tuned.